This, I believe, is the final exam practice worksheet that we put out. And we want to look at D and E. D is the easy one, so let's do that one first.
What page?
I don't know, flip to page number 31. It's in the practice, 2B practice problem worksheet, posted online on SmartSite. I don't know, it's a couple pages, there's only like 5 pages, so 31 should be hard to find. Okay, how do you find the optimal pH? That one's easy. You look at the Ka, take the negative log of it, and that's the optimal pH. Done. Okay, E. And you can always do that for a buffer. That's it. Okay. What's the pH at the stoichiometric point? Fill in the table below for this one. This is, let me say this and see if this is helpful. You know, earlier, if you were here earlier, we did the problem with I made up a weak acid and KOH. I did the stoichiometric part of the problem for the equivalence point. Same thing. So take a look at that first. If you're still confused, ask me at the end. Okay, who's next? Yes, right there. Whoa. I think some people are lucky to be alive right now. Okay. All right, what kind of problem do you want? Do you have one for me?
Number 13 in that same package.
Oh, can you pass it to me? Sorry, I didn't bring it today. Number 13, though, we're looking at in the same packet. Okay. Let me just see if this one applies. Yeah. Let me see. This one does not apply to what he's asking. It kind of is there, but it's not exactly what he's asking. Okay, pass this back. Let's just kind of do a quick, let's say you have A and B. You would need the partial pressures of A and B. So let's say 400 torr and 300 torr, something like that. And you need the moles of each. So let's say this is moles of A is 1 and moles of B is 3 or something like that. And so in order to do for the Raoults, we could ask you like what's the partial pressure of A? Well, that'd be the mole fraction of A times the pure pressure of A. So the mole fraction would be 1 over 1 plus 3 times 400, which I guess is 100. Is that okay? This is the partial pressure of A in the mixture. This is partial pressure of A all by itself. Okay? PB, same sort of thing, XB times PB, which would be 3 over 1 plus 3 times 300. That would be not as nice of a number. That'd be 75 times 3, is that right? So 225? Okay, I don't know where all of you went. PA plus PB, if it's not, tell me. You need P total then, which is, if I'm right, 325 total. Okay? And then, so here's the mole fractions in the solution. 1/4 and 3/4, is that okay? That's in the solution for Raoult. If you want the mole fraction above the solution, so XA above the solution in the gas, that's Dalton's law. And that's P total in that equation. So you do the same PA 100, but divide by P total, say it's 325, and whatever that number is. So this is the Dalton law part of the problem, because I wanted the mole fraction above the solution. Okay, who's next? Yes?
Can you do number 13?
Okay, that problem you just showed me. Okay, what part? What part? the mixture. Okay, and because we have information in the mixture, we're using Raoult's law right now. Because if information in the mixture is Raoult's law, if we had information above the mixture, we'd use Dalton's law. Okay, so for part B, same deal, except he just took it a step further. So it's the partial pressure B. We need the mole fraction of B and the pure pressure of B. The mole fraction of B, the ratio of A to B is 1 to 4, it says in the question. So that means, let's say if we assume 5 moles, then there's the moles of A is 1, and the moles of B is 4, right? Because they're in a 1 to 4 ratio. So you could use this to find the mole fraction. XB would just be 4 over 5, or 0.8. And then you just need the pure pressure, and let's see if we have that. We know the A, pure pressure. For this one, this is kind of how you'd actually do part A, for A. For B, they actually don't give you the pure pressure, at least I'm not seeing it right now, and they don't give you much information about B. So what I probably do, since you have a container, this is A and B in here, they have a partial pressure of A and a partial pressure of B up here. What I probably do is, for part A, you get this. And I think from part A, you should find P total as well. So P total is PA plus PB. That's how I do part B. For part, there's no part E. Did you say part D?
Yes.
Okay. For part D, predict the normal boiling point, and they give you a delta H of vaporization. I'm thinking Clausius-Clapeyron immediately, because we're talking. Normal boiling point is a key word for Clausius-Clapeyron, and so is delta H of vaporization. You want me to write that stuff down?
No.
Oh, okay, cool. Hi.
So partial pressure and vapor pressure is the same thing?
Yes, partial pressure is the same as having a vapor pressure. They're both pressures, just different ways of verbalizing. Yes, next, yes. Okay, practice exam, page 91. Number 27B. Let me see if I can find that here. Okay. So I'm assuming you can do 27A. So let's write out this reaction. It's PbCl2. So you should be able to write that out for this kind of question. This is looks like an ice table sort of question. And you're adding sodium chloride. You're adding, that's a common ion question. So I'll just say you have a certain molarity there. I don't know what it is, but I know I'm adding stuff to it. And then, at this point, it looks like I don't have any of this, and I'm going to ignore that. Is that okay? So I shift to the right, plus x plus 2x. Okay? And then this is x and m plus 2x. And then I know KSP is equal to x times m plus 2x. Okay, let me change colors now. This is known, KSP, is that all right? M is not known in the problem, but X is known. X is given as 6.3 times 10 to the minus 80. So I'm going to solve for molarity of the initial concentration of the chloride and then convert to grams of sodium chloride to solve the problem, just through conversions. Is that okay? So solve for M, and that's just molarity of chloride. And convert then to grams of NaCl. Is that okay? Yep. It's given. Both KSP and X are given in law. No, it's given in part B. It says 6.3 times 10 minus 8. I just read it off the page. Okay, next. Oh my gosh, way back there in the back. Okay.
Oh, wait, for that question, was that supposed to be squared, the n plus 2x?
Sounds great.
Okay.
Square. I forgot. Okay. How does solubility affect pH? Yeah, this is good to clarify, especially when you're looking on some of the older final exams. You're going to see, okay, let me just do in general first. Let's say you have mx. Okay, this is the part that you'll see common in the older exams. If you look at this, if this is not neutral, okay, that means anybody, it's what? Acidic or basic? If that's not neutral, then it is not acidic. Any other guys? Oh, good. Why? Okay, I'll say this. It's an anion. Does that help? Okay, no. Anions have negative charges. Does that help? So why is it basic? It has a negative charge. Yeah, it's a proton acceptor. That's the Lewis definition of a base. So anything that's negative is typically a base. Remember when we did that stuff in chapter 15? Actually, it's the acid, base, or neutral. We separate out the ions. And the anion is always neutral or basic. The cation is always acidic or neutral. Same thing. Okay? So if that's not neutral, then it's basic. If it's basic, therefore, thus, you can add an acid to this to make it more soluble. Adding an acid, remember, is the same thing as decreasing the pH. This is a common multiple choice question in the old finals. Okay? There's something else that is also true that the old finals do not consider for various reasons. Okay? That you can ask me after if you're really curious. But it's also true, and this is not true in the old finals, but it's also true that if this is not neutral, then it's what? Why? Because it's a cation, has a positive charge. It's an electron pair acceptor. That's a Lewis acid. So if that's not neutral, then it's acidic, and then thus you can add base or increase pH to make it more soluble. The part in purple here that I just wrote is not considered in the older final, so don't consider it yourself either. But it's true, it would be true now if you saw it in a current final. So you can add an acid or a base to make something more soluble. Increasing pH or decreasing depending on what these are. Let me ask you one more question. How do you know if it's neutral? Anybody? It's a conjugate of a strong. Yeah, that's how you know if it's neutral. Then the rule does not apply. Can't apply if it's neutral. Yes? What if M and X are both acidic and basic? Then you could do either. Both would work. Yeah. Now let me say one more thing to that. This in purple here would be a complex ion problem, Kf. Because this would be a transition metal, and you'd be adding, like I added to the iron, I added cyanide. That was a base, and I formed a complex ion. This here doesn't have a particular kind of category, but it would be a KSP comboed with an acid problem, which you haven't seen very much of, but you've seen now a couple of these, both in class and attempted one today. Okay, next, yes? Hold up, 106, number 50, no, 15 probably, okay. We've got KSP for this compound right there. Let's zoom in a little bit. We know that concentration, So what pH requires to start the precipitation? Oh, this is a category we didn't get to, but it's precipitation. That's the key word in this problem. Precipitation. So, once I see the word precipitation, am I thinking ice table, yes or no? No. You could use the ice table, but you don't have to. Okay. So, here's how I would do it. And here's what you're thinking. When something is just beginning to precipitate, or the opposite, just beginning to become soluble, that means it's at equilibrium, because that's the saturated solution. And so if you're at equilibrium, you don't need an ice table. So all you do is say, well, I've got Mg, I think it was OH2. So KSP is Mg2 plus and OH minus squared. KSP is given in the problem and Mg is given in the problem. Solve for OH. And that's the concentration needed for precipitation to begin. Oh, and then once you have that concentration, just convert it to a pH. Yes?
Why do we multiply the OH by 2? Why do we multiply by 2?
Oh, why is there no multiplication by 2? That's right, there's no ice table. So if there's an ice table and there's a C line, then there better be a 2 in there somewhere. Or if you're doing stoichiometry, there better be a 2. But in this case, the only 2 is the square. Okay, you had a question already, so I'm going to move around. Yes, right there.
Page 148, number 18.
What?
148.
48.
Wait.
Page
Hold
148.
up.
And the.
Okay, I only go up to 123. That is amazing. We need her secret stuff. Can you give me a year? Oh, you can come down here. Yeah, I guess that's true too. Hi, welcome. Nice to meet you. What's your name? Hi, Rebecca. How's it going? Is this your first quarter of my class or second? Get me for 2A, second quarter. This is Spring 06, number 18. Spring 06, number 18. Let's see. KSP equals 1.1 times 10 to the minus 12 for this compound CuI. We have the concentration of copper, 0.01 molar. We're adding to this solution Ki, and I want to know how much Ki do I add to this solution to cause it to precipitate. Okay, what kind of problem is this? Let me ask the other way. What was the key word? Precipitation. Do I use the ice table? No, not necessary. So, all I'm going to do, Rebecca, is write KSP is Cu times I minus. I know this. I know this. Find this. Is that okay?
Yeah.
And then convert that to mass. Is that part not okay?
That's fine.
Oh.
I thought this was a special problem where you had to find it.
You thought it was a special problem?
I know, threshold. We had to find it.
I don't think so. Yeah, I think that'll do. Cool. It's less crazy than you thought. Way back there, the two buddies sitting together.
Can we spring 2003 number 1?
Spring, hold up.
It's page 109.
Ah, that's what I wanted. 109, that's easier. Number 3, you said?
Number 1.
Number 1. That's this problem with the nickel. 109. Okay, nickel is placed into water. It's 1 liter of water. It's 25 degrees C. There's 100 grams of the nickel. And this is at 150 degrees C. And the T final, after it's dumped in there, is 26.3 degrees C. I want to know the specific heat of the nickel. Okay, so this is a heat problem. I know that because two things are mixing and there's a final temperature. Is that okay? So you go sum of the Q's equals 0. You're going to have a Q for every temperature change and every phase change and every reaction. When there's no reaction, there's no phase change. So just Q's for temperature changes. So you want to find everything that changes temperature. So the nickel will cool down. The water will warm up. And that's it. Okay. So 0 equals Q of the nickel, MCP delta T, that's for the nickel, plus the Q of the water, MCP delta T. Okay, the term I'm looking for is where I just put the arrow. Everything else is known. So 0 equals the mass of the nickel, 100 grams. The CP of the nickel is what I want. The temperature change, this is the tricky part. The temperature change, T final, remember, always first, minus T initial, 150. And then plus, mass of the water. This is pretty common that they don't give you the mass of the water, they give you the volume. So what you're going to do is say 1 liter, convert this to milliliters, and then use the density given on the back of the exam, 1 gram per milliliter. Now it's in grams. Oh, you look very happy about that. CP is 4.184 joules per gram degree C, and then the temperature is 26.3 minus 25 was the initial. If you don't get these T finals and T initials right, that'll mess you up. And of course, if you didn't know that density times volume is mass, that would be a problem too. Okay, cool. All right, next. Oh, cool. Oh, I thought we were done. Yes, Sam. 88. This one. Okay. Number 6 here. Okay. Relative acid strength. So this is like Sesame Street. What is not like the other one? So you need to compare and contrast. Notice that the only difference, I think, is the location of the CL. And I think we even bolded it just to make sure you can find it. Okay? You see that? Okay. So the CL, this is what effect? There's 4 factors. What's the one that this one is? Inductive. So the Cl that is closest to the acidic hydrogen, where the Cl is closest, that will cause the that one to be the most acidic. So where is the acidic hydrogen? Is it on the right, the left, or middle? It's on the right. It's this one, or that one, or that one. How did you know that? Why is it the one on the oxygen and not the one on the carbon? Because according to the periodic table, the more right you go, oxygen is more to the right of carbon, the more acidic you are. So it's the one on the right, and then I would pick the one that's the most acidic, is closest, the Cl is closest to it. That's it. Okay, who's next? Yes? Hi. 102, number 32. 22, maybe. Oh yeah, don't worry about this problem for the exam. Okay, cool, that was easy, yes. Okay, probably about 2 or 3 more problems and then we'll be done for the night, depending on how difficult this one is. Okay, that's what I'm hoping for. I look smarter when the problem is easier. 41. Oh my gosh. Oh, okay. This is kind of like what we're talking pH and solubility. Whoever asked that earlier. Okay. Which of the following will increase the solubility of PbS? So remember that compound. Oh, let's think about it. Is Pb, will that be a Lewis acid? Or is it neutral? Is it the conjugate of a strong? How about that? No. So is it acidic, basic, or neutral? Just the PB. If it's not neutral, it is acidic. How about the sulfur? Is that neutral or basic? Basic, because it's not the conjugate of a strong. So either adding a base to this one or an acid to this one should do it. Okay, you think it's A?
No,
Oh, okay. Freaked out about that. There's several possibilities. It's not C or D. E just sounds ridiculous. So A or B could work, and it depends if we were thinking, really A or B could work. Let's see if, wait, what number was that? 41. 41, they picked A. Oh, you were right. Yeah, good. Yeah, but B could actually work too. Yeah. So technically I would accept A or B. Okay, next. Yes, Alex.
119, 21.
Oh, what's the page again?
119.
190.
19.
119. What number?
21.
21. Oh gosh. Okay. This one, right? Yeah, no wonder. Okay. Let me set it up for you. I'll let you solve it, okay? This is not an unusual problem though. The copper problem I did in class 2 classes ago is identical to this one. Okay. So this is a complex ion problem. I know that because there's a KF given. I should be able to write this reaction. And in reality, I forgot if I just said this, but this is not an unusual problem. So there's the reaction. I need to balance it. And then I have 0.02 of this and 2 of this. I'm not given the volume, so this would be these could be moles, or if the volume says 1 liter, then this could be moles or molarity. Okay? Now, but equal volumes of them are mixed. So what's going to happen to molarity? Half. Equal volumes are mixed. I'm doubling the volume or half the molarity. Okay. Now, I could put a 0 here. Some people might think I could start the ice table now because I want the equilibrium concentrations, but I can't do that because I need a 0 on the unfavored side. Yeah. So minus 0.01. Oh, whoever was asking me up here, they probably left and they'll regret it now. See, here's the 4. Here's a place where when the limiting reactant is smaller, it's easier to do the problem. And when there's no coefficient here. See, because this is this times 1. And this is this times 4, so it works out. If it was flipped for some reason, then that would make it a little more crazy. Or when I'm subtracting, whenever I'm subtracting from something that doesn't have that has a coefficient here, like that hard problem I made up. So plus 0.01. This is going to be your I line now. This is the I line, Alex. Okay? Okay, you're going to go through and do stuff like that. You need the concentration of the zinc at equilibrium. You need the concentration of zinc at equilibrium. Why do you need that, you wonder, Alex? I know you're wondering that. Because this is KSP. And so if you know this from the ice table, and this is given, you can calculate, actually you'll calculate Q and compare it to KSP. And depending if it's larger or smaller, that'll tell you if it precipitates or not. Okay, cool. Yes? Okay, this might be the last one. Okay. Hello, welcome. What's your name? Abdul. Okay, nice to meet you. Is this your first part of my class? My last one. Oh, yeah, right here. This part. That's what all the kids do now.